Hello and welcome to part 2 of our deep learning lab, which is focusing on building segmentation. If you've just joined, this series walks you through building a semantic segmentation pipeline using U-Net and TorchGeo in Colab. So in part 1, we prepared our geospatial dataset. Now we want to build the U-Net architecture, train the model, monitor loss and accuracy, and then apply early stopping to avoid overfitting. So why are we starting with U-Net? U-Net is one of the most popular deep learning architectures, which is used for semantic segmentation. So it uses the encoder and decoder structure. So the encoder captures the features like shape, texture, and spatial context, while the decoder restores the original image resolution while using the skip connections in order to retain the fine details. So this is important when we want to extract building outlines. So U-Net is also very important because it works well with a relatively small data set. So this makes it ideal for remote sensing tasks such as extracting building footprints. Right, so here we're going to start by defining our U-Net model here for segmentation in PyTorch. So we are going to use the convolutional blocks with the ReLU, max pooling, and we are also going to use the transposed convolution that we use for upscaling. So this model is going to output a two-class prediction for each pixel, so that we have a building or a background. So that is a building footprint or just a background, which is 0. So as I said, this is employed. We're going to employ here a custom PyTorch module, which is called U-Net, and this inherits the nn.module. So yes, the architecture follows the encoder decoder structure. So the encoder consists of 4 convolutional blocks. So you have here the first encoder, then the second encoder, third encoder, and then the fourth encoder. And each encoder is followed by a max pooling. So we have max pooling 1, 2, 3, and 4. So this reduces the spatial resolution and captures the increased linearly abstract features. Right, so each encoder block is created using the function CBR. Okay, so this function just stands for convolution, batch normalization, and ReLU. Okay, so ReLU, remember we said this is the rectified linear unit, okay, which is just an activation function. And so the helper function here, the CBR, applies 2 convolutional layers with padding in order to preserve the spatial dimensions, and the ReLU in order to do like a non-linearity in the model. And the batch normalization is a technique used to stabilize and accelerate the training of deep neural networks. So it works by normalizing the inputs to each layer. Okay, so here we can use the batch normalization by adjusting and scaling the activations within a minimum batch, so that they have a mean of 0 and a standard deviation of 1. Right, so let's take a look briefly at the encoder. So as I said, each convolutional block is defined using this CBR, this helper function, which is a CBR. Okay, so what do we have? For example, here for our CBR function, which is the convolution batch normalization in ReLU. So we start with an input which takes 3 channels. So these are the RGB bands for our input image, right? And then it's going to output 64 feature maps. Okay, so that is the 64 feature maps comes from applying 64 convolutional filters to the input image. So remember, when we did an earlier tutorial, we talked about convolution as filters, right? So these blocks are going to learn to identify spatial patterns such as the edges, textures, and shape. So following each CBR block here, so we have a pooling layer. So this is a pooling layer which performs max pooling within a 2x2 window. Okay, so the 2x2 window, this operation downscales the feature map. Okay, that is it's going to cut the height and width in half while preserving the most prominent features. Okay, again, so as we go deeper into the model, okay, we have more of this operation taking place, and more of the max pooling happening to downscale the resolution. Right. Okay, so next, after this encoder, we go to the middle part of the U-Net model. Okay, so at the center of this, we have a bottleneck layer. So this is a bottleneck layer. So this acts like a bridge between the encoder and the decoder. So it's acting as a bridge between the downsampling and the upsampling. So take note that this layer is the highest number of filters here. We have 1024. So it means that it can learn and store a large amount of abstract information from the input image. While the earlier focus on simple features like edges or textures, the bottleneck here captures more complex and high-level patterns so that we can identify the building outlines. Right. So it is very important because it summarizes the most important feature before the coder reconstructs the segment output. Right. So following that, we have the decoder, the upsampling. Okay. So the decoder just mirrors the encoder, but it gradually upsamples the feature maps using the transposed convolutions. Okay, so we have the upsampling here. This is our upsamplings from the decoder. Right, so what do we have? So at each decoding level, the upsampled features are connected with the corresponding encoder features via the skip connections. I'll show you in a minute what these skip connections are. So this is going to help to retain the spatial context. So these connected tensors are passed through the decoding blocks. So decoding blocks, this means that decoding block 1, 4, 3, 2, and 1. So again, we are using the same CBR functions to do that. And then finally we have a 1x1 convolutional layer named final, which reduces the output to 2 channels. Okay, remember now we've got 2 channels. So this represents the class logit for background and building for each pixel in the patch. So this modular design ensures that the spatial details are preserved while learning abstract features or abstract representations. So this makes U-Net effective, especially if you want to do some precise segmentation of the building outlines in an aerial image or a satellite image. Right, just after that we have this forward method. So it's just defining how the input data goes through the U-Net, this U-Net layers. So this is what this forward method is. So it's just describing the encoder, the bottleneck, and the decoders. Right, so this is an example of what we'll be looking at, as I have been talking about. So we have here our encoder, and then we have the bridge. Okay, so the encoder here responsible for the downsampling, and then we go up to the decoder, which is responsible for the upsampling, and then we have our output image. And then these are the skip connections, so connecting the encoder with the decoder. This is our skip connection. So this is just a sample of the U-Net model. Right, so next let's initialize the key components needed to train the U-Net model. So this include the model itself, the optimizer, and the loss function. Right, so in this code we create the U-Net model and assign it to run on a GPU. So this is the option if the GPU is available. So in Colab you can get to use a GPU. So we are going to select the Adam optimizer because it is very efficient, and it can be adapted. Okay, it's very adaptable, and we are setting it here to a learning rate which is very, very small, about 0.001. So that's the learning rate. So remember we previously talked about this optimizer Adam. So I said this is called it refers to the adaptive moment estimation. So adaptive moment estimation. So this optimizer is widely used as an optimization algorithm in deep learning, as I said, because it has got speed, stability, and adaptability. Okay, so why do we use it? Because it takes the benefits of 2 other methods, that is momentum and RMS prop. So momentum helps accelerate training by smoothing out the updates based on the changes that happens. And then the RMS prop adjusts the learning rate for each parameter. So based again on its on the frequency it changes. So these two are very good because they keep a track of the average of the gradients and the average of the squared gradients for each parameter. Right, so this is quite good to use the best of both worlds. Okay. Right, so let's look. So this is going to what else do I need to talk about? Here we are going to use cross entropy. Okay, so cross entropy. This is because we are dealing with a segmentation task here. So where each pixel is classified as a building or a background, and then finally we use the summary function here, so that we can print a structured overview of the unit structure. So the structure is going to show us the number of parameters in each layer and the size of the feature maps, which help to confirm if the model setup was correct. So this is just the structure of the unit model after we print the summary. So we can see the layer type, we can see the output shape, and then we can see the parameters. Okay, so these are the parameters of the model. So it's quite huge. Okay, we have a lot of parameters, about 31 million parameters. Right. Okay, so next we want to talk about the training now. So this is very important. So we are going to implement a training loop for the unit model that runs up to 20 epochs, and we are going to incorporate here early stopping to prevent overfitting. So the goal is to monitor model performance and stop training once the validation loss stops to improve the model for the specified number of epochs. Okay, so defined by the patients here. Sorry, by the patients here. Right. So what happens here is that first we are going to initialize 4 lists here. So the train losses, test losses, train accuracy, and test accuracies. So this is going to record the performance matrix over time, and we are going to set up early stopping variables. So we have the best var loss, so we set it initially to infinity, and then we have the early stopping, which is going to track the consecutive non-improving epochs, and then we set the patience here to 5. Okay, and then we are also going to define a path for saving the best model. Okay, so the best unit model, so that we can reuse it later. So during each epoch, remember we have 20 epochs, so during each epoch the model enters training mode using the model.train. So this enables layers like dropout and batch normalization to behave appropriately. So it then iterates over the training data set in batches. Okay, so for each batch, only the first 3 channels of the image tensors are used. Okay, so we are saying the first 3 channels here. So this is the RGB input, and the batch is passed through the model to obtain the predictions. So then the loss between predictions and the reference mask is computed using the cross entropy criterion that we said we are going to use. Right. So the standard propagation is performed here. via the loss backward, followed by a weight update step, okay, which uses the optimizer. So the total loss and number of correctly predicted variables are then tracked to calculate the training accuracy. So once the training loop completes, the model switches to evaluation mode with the mode evaluation, and it's going to disable the gradient tracking using the here the torch grad. Okay, so this is going to improve efficiency. The model then evaluated on the test dataset in the same manner as during the training, but here without updating the model weights. So the validation loss and accuracy are computed and then stored. Okay, and then finally we are going to apply the early stopping logic. So if there's no improvement, the early stopping counter increases. When this counter reaches the defined patience threshold, say of 5, so 5 consecutive non-improving epochs, then the training loop is terminated early. So this mechanism reduces overfitting and ensures that the best performing model is retained. Right. So following that, so we can see the training of the model. Okay, here you can see the train loss, the test loss, the train accuracy, and then the test accuracy until the model stops. Right, so after that we can visualize the accuracy and loss. So we start by visualizing the training and test loss. As you see, we have initially the training loss going down, and it's going down gradually, which is good. And then we also have the test loss going down, but then after hitting this epoch just after 15, then it is going up. So that means there's something which is not going right here. Right, we can also visualize the training and test accuracy, and as we can see, training accuracy is increasing as the epoch increases. The same for the test accuracy, and we have actually a small gap, so our model is not really affected by overfitting or underfitting. So quite a good performance for such a small data set. Right, so I think this is all we can do for until now. So for this first part, so what we have done so far, just for a recap, so we have built a custom U-Net model, and then we have initialized training with the cross-entropy loss, and then we have trained using early stopping. We have also have monitored the loss and accuracy, and we also saved the best model for inference. Okay, so we will continue in the next video, so that we now can run the model, and then we can run the model based on we can run inference based on the best model. So see you in the next video of this series.